Good morning, everyone. This is Yoshinari Motokawa speaking from Waseda University in Tokyo, Japan. Today, I'm going to present a proposal for interpretable multi-agent deep reinforcement learning model, namely Mat-Dqn. This is the outline for today's presentation. The first one is the general background and current issue of my research theme. Let me first briefly talk about what multi-agent deep reinforcement learning is. It is a study of a system in which multiple intelligent entities or agents interpret each other. Particularly, we focus on multiple agents that aim to achieve some goals under reinforcement learning structure. Although the deep reinforcement learning technology has contributed significantly to multi-agent systems to build coordination among agents in complex environments, it is still unclear what information the agents depend on to behave cooperatively. This issue is called the black box problem. Here, our goal is to remove such ambiguity in order to further improve the efficiency and productivity of multi-agent systems. There are several genres for research about establishment of explainable reinforcement learning. Reward decomposition is a method to analyze a component of Q-value calculation to see what reward element is significant, as shown in Figure 3. Gradient information is also useful to see what part of input information is sensitive with respect to output, as shown in Figure 4. For our research, we particularly focus on the attention mechanism to clarify the unknown decision-making process of agents. Next, I'd like to introduce some previous research that work on the attention mechanism in multi-agent system. There are a few studies on the interpretability of the behaviors by multi-agent deep reinforcement learning. According to our survey, most of previous research mainly focuses on the intra-network among agents by adopting the attention mechanism. For instance, agents with attentional communication model pays attention on only communication between others. Agents with MAAC method pays attention on only information from other agents, and neither model pays attention on tasks. Therefore, our goal is to make the agents capable of paying attention on both agents and tasks, so that we can interpret the coordinated behavior of agents based on their attentional heat maps. Now I'm explaining the proposed method in this section. We introduce a novel approach for improving the interpretability of the multi-agent cooperation. The proposed method, the multi-agent transformer DeepQ network, is derived by incorporating the transformer encoder into the DeepQ network architecture, as shown in figures 8 and 9. By analyzing the compatibility of vectorized information called class token inside the multi-head attention of the transformer, we can interpret what information is really influential for the agent's decision-making process behind their coordinated behaviors. Note that each agent owns its independent network for the decision-making process. Here, I'd like to explain the conducted experiments and results in detail. We conducted experiments to investigate the performance and advantages of the agents using the proposed method, Mat-Dqn, in the patrolling task, which is a coordinated object collection game on a grid environment, as shown in Figure 10. In this collection game, 8 agents are initially placed at the center of a map, as shown in the blue boxes, and they start exploring the environment to collect objects that randomly appear in the beige objects area. At each step, agent goes toward one of directions, right, up, left, or down. Once agents collect the object, positive reward is given. On the other hand, if the agent hit the walls or other agents, they gain negative reward instead. Other hyperparameters used in the experiment is shown in the table. This is an expectation of how agents observe the environment. Each agent individually observes the environment, and agents cannot see objects behind the walls or site. Figures 11 and 12 demonstrate the example environment and example observation of red, blue, and green agents whose visible site is set at 7. The observation is encoded in either -1, 0, or 1 at certain channels, depending on the types and existence of the entities. In the experiment, we tested two types of different observation methods, namely local view and relative view method. For local view method, agents encode the observation in 3 times 7 times 7 discrete matrix, as shown in figure 13. For relative view method, agents encode the observation in the size of entire grid map with 4 channels. By doing this, agents with the relative view method know their global position. This is a quantitative result of comparison in 4 criterion: number of collisions against walls and agents, number of collected objects in each episode, and the mean episode reward. We compared these results of our proposed method Mat-Dqn with the vanilla Dqn as a baseline as shown in blue and red lines respectively. According to graphs A and B, both count of collisions decreases across the training so that we can say that agents succeeded in collision avoidance besides the difference of methods. Also, our proposed method exceeds in performance as the depicted blue lines achieve 12.2% better for object collection count and 13.2% better for episode reward that are shown in figures C and D respectively. In addition to performance comparison, we generated the heat maps based on the output from attention heads of some agents and analyzed which types of information in observation each agent focused on. Such analysis helps us understand the agent's decision-making process after sufficient training. As a general idea, we find that agents usually pay attention on both agents and objects if they are seen in the observation but not on the walls. We compared the attention heat maps of 2 agents, A and B, as shown in figure 16. Note that white boxes indicate wall, yellow boxes are the objects, and blue is agent. The observing agent itself is shown at the center of its observation. According to A's point of view, it pays the highest attention on the adjacent object because the immediate reward is expected by going toward the right. From agent B's perspective, on the other hand, it focuses on the other agent A. This is because the decision-making process of the agent B strongly depends on the strategy of other agent. Moreover, we analyzed how the cooperative behaviors are associated with the generated attention heat map. The observations and heat maps on the right side in these figures are the state at the next time of those on the left. We also annotated the heat map with the attentional weights. In the first case left side, agent A saw 2 objects located on opposite sides. Thus, it moves toward right in order to approach the closest object. We can recognize A's action from the attentional heat maps as well, because the agent pays the attention to 2 objects with 0.189 on the closest object and 0.112 on the second closest. After moving to right side, the attentional values changed to 0.220 and 0.109 respectively. We can observe the coordinated behavior in case 2 right side. Based on the observation B, there were 2 objects located on opposite side as in case 1, and another agent B was located near the closest objects. Thus, agent A moved downward so as to approach a further object. This behavior seems rational in the sense that after leaving the collection of the closest object for another agent, agent A headed for the object in a different direction. This action also reduced the possibility of a collision. The heat map of the attentional weights explain the situation as well. Agent A put the highest attention on the closest object, and at the same time, Agent A focused on B as well. Because we can expect that attentions on the other agents work in the repulsive way, the attention mechanism directed Agent A to the object below. This discussion indicates that we could succeed in visualizing the source of information in the decision-making process of the learned agents by using the proposed Mat-Dqn method. Finally, we investigated the cooperative and collaborative behaviors with the learned policies from a macro perspective. For this purpose, we conducted 1,000 episodes of the same experiment after training and generated the heat maps indicating where each agent collected objects. The result maps of 8 agents are illustrated in the figure 18. This figure shows that a pair of agents were equally distributed in each room, and the room was divided horizontally. Thus, we can say that agents individually trained without any communication and succeeded in taking charge of their respective divided region in a bottom-up manner. Furthermore, we compared the training performance of agents using the relative view method. Similarly to agents with local view method, agents of proposed method and baseline with the relative view method succeeded in training. According to the graph, we verified that Mat-Dqn agents performed approximately 15.4% better with the relative view than those of the local view, although the performance of the baseline agents with the relative view decreased approximately 2.3%. These results suggested that the Mat-Dqn agents could utilize the additional information in the relative view, whereas the baseline agents could not, but rather were confused and could not learn sufficiently due to the greater amount of data in the relative view method. Again, we generated the heat maps based on the output from attention heads of some agents with the relative view method. Note that we applied rough attention patch size on the observation in order to cut the calculation cost. According to the observation and the corresponding attentional heat map, agents indeed focuses on only visible region. We believe that exceeding performance achieved by the proposed method is derived from this feature. This is the object collection heat map for each Mat-Dqn agent with the relative view. Similar to the previous result, a pair of agents were equally distributed in each room. Remarkably, the room was clearly divided horizontally because agents succeeded in utilizing the additional information with the relative view method. This is the conclusion. We propose to use the attention mechanism of the transformer architecture for multi-agent deep reinforcement learning, which allows us to more clearly interpret the policies and behaviors learned by the agents, as well as to identify the information that is important to them during the decision-making process. It also enables agents to learn more efficiently and act more effectively by eliminating the unnecessary information. This is it. Thank you for listening.